Bismillahirrahmanirrahim. The topic today is solution of FE equations by Cholesky decomposition. Now this Cholesky is a form of LU decomposition, but it can only be employed in cases where your matrix is a symmetric matrix. Since the K matrix that we encounter in FEM, at least in the case of stress analysis problems and some other problem also, but for stress analysis problems this K is symmetric. So instead of the usual LU method where you convert this matrix into a lower and upper triangular matrix, you can employ the Cholesky decomposition method where you convert this K into a lower triangular matrix and an upper triangular matrix that is nothing but the transpose of the lower triangular matrix. This can only be done for symmetric problems, and obviously if your system is not symmetric, you'll have a certain computational cost for this kind of operation. But if your system is symmetric, then your computational cost is reduced by 50%. So in view of the fact that the stress analysis problems and some other problems also, you encounter K which is symmetric, it makes all the sense in the world to employ Cholesky decomposition method. So what we do here is whatever the values of K, for example, let's put some variables here. I'll just demonstrate the process using a 4x4 matrix, but you can extend that to any size. There's a certain kind of pattern here which is very easily identifiable. So this is your system. You need to calculate the 4 displacement values, and you have four force values here. So the goal here in Cholesky decomposition is to convert this system into a lower triangular matrix, and that will be something like this. You'll have 0 values here, and an upper triangular matrix. Symbolically it will be something like this. All zeros, you'll have values here, but all 0 values here. It's the transpose of this. So this is the lower triangular matrix, and this is an upper triangular matrix which is actually the transpose of this lower triangular matrix, and the rest is the same. So the first step, let's call it step 1, is this. Once you have, and you can express this in this form. Let's call this x vector. We don't know the value of x, but when you multiply this matrix with a vector, you should get a vector of the same size. Now we can write this as which is x1, x2, x3, x4. We have some values f1 to f3, f4. Now you are familiar with backward substitution and forward substitution in your lecture on Gauss elimination. So here you can use forward elimination, because here is just one number multiplies with this to get f1. You can get x1, and then next step you move on. So you calculate x1, x2, x3, x4 are calculated by forward substitution. Let's call this step 2. But we don't need x1, x2, x3, x4. We are actually interested in u1, u2, u3, u4. That is not difficult, because recall that we had written this in this form. If we have the value of x now, x values are known, so what we write is step 3. Step 3, let's write this as L transpose U is equal to x. So this now serves as the right hand side. That is x1, x2, x3, x4. Here u1, u2, u3, u4. These are the values that we want to calculate. And this one is now an upper triangular matrix, which is nothing but the transpose of this matrix, and all zero values here. So now here we did forward substitution. Here you can easily calculate. These are known, these values are known. You can calculate u4 first, then u3, u2, u1. So u4, u3, u2, u1 are calculated by backward substitution now, and that gives you the value this that you sought to find in the first place. So basically there are 3 steps. The first step involves conversion of whatever K matrix is, and here we just show it on a 4x4 system. We are going to show it on a 4x4 system, but it doesn't matter what size of the system is. You convert this into a lower triangular matrix and upper triangular matrix, which is the transpose of the lower triangular matrix, and this is only possible when your K matrix is symmetric, and this will reduce your calculations by 50%. The next step is simply calculation of one vector by forward substitution and the next vector by backward substitution, and this last vector, this is what basically is the purpose of the whole exercise. Let's take up a numerical question and give values to these variables and see how we proceed. We are going to take a 4x4 matrix. As you can see, this is a symmetric matrix, as your K will be for stress analysis problems and for many other problems as well. You have to use. So the first, step 1. In step 1, we have to convert K, this K matrix, into lower triangular matrix and an upper triangular matrix, which is the transpose of the lower triangular matrix. This is actually U. Let's write it down like this: 5, minus 4, 1, 0, minus 4, 6, minus 4, 1. This is just a reproduction of the values here. As we are going to start the first step now. Symbolically, in terms of variables, L11, L21, L31, L41, L22, L32, L42, L33, L43, and L44. These values will be 0, 0, 0, because this is the lower triangular matrix. This is your principal diagonal, so everything above it is 0. Now this, because in the next one is simply going to be the transpose of this, so you can write it like this: L21, L31, L41, 0, L2. You just transpose this here: L22, L32, L42, L33, L43. So we have here we have this is the principal diagonal, and everything below it is 0, and this is this one is transpose of this. Each is a transpose of the other. So let's see what values all these positions assume if we multiply them. This becomes L11 square. This is L21, L11, L11 square. The rest are 0, so 0. This is L21, L11. And the next there's L22, but all are 0, so this takes this form. This L31, L11, this is L41, L11. Similarly here we have L11, L21, L21 square plus L22 square, L31, L21 plus L32, L22, L41, L21 plus L42, L22. Third one, we are just taking the product of two matrices. Third one is, please verify these calculations, L11, L31, L21, L31 plus L22, L32, L31 square plus L32 square plus L33 square, L41, L31 plus L42, L32 plus L43, L33. And the last one, L11, L41, L21, L41 plus L22, L42, this one by this, the rest are 0. Then you have L31, L41 plus L32, L42 plus L33, L43, and finally L41 square plus L42 square, L43 square plus L44 square. So for your right hand side to be a lower triangular matrix and an upper triangular matrix, which is the transpose of the lower triangular matrix, each value, each position takes this value. Now if you see, this is a symmetrical system. L21, L11, L11, L21, same thing. L31, L11, L11, L. So this is completely symmetrical. So if it's a symmetrical system, then anything above it is just a repetition. You can just focus on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 quantities, and you should get your you can proceed, because the rest is just the same, as is the case here. If you write it like this again, 5 minus 4 1 0 minus 4 6 minus 4 1 1 minus 4 6 minus 4, this is the principal diagonal. Anything above it is just a repetition of anything below it, so you don't need to consider that. Now what we are going to do is equate each of these values to the variables here and find the values of those variables. We don't need to do it for these values because we would have already done it here. So this is just a repetition, as is the case here. Whatever is here is also there, so you don't need to do it twice. So this is where the 50% reduction of calculations takes place. If it was a simple LU method, you would have some values here obviously, but then those values would have been different. It would have been a U matrix here, but it wouldn't have been the transpose of L. So these values would have been something else. Here you would have written not L11, L2, but U11, U12, U13, etc. These would have been different, and that would have been necessary if this matrix was not a symmetric matrix. Because this is a symmetric matrix, you can get away with this kind of a thing, and you can reduce your cost considerably. Now what remains is simply find the values of these, and your step 1 will be complete. So let's start. L11 square is equal to 5. This is equal to this one. This implies that L11 is equal to 5 under root. And for positive definite matrices, you just take the positive sign. Don't worry about the negative sign here. L21, L11 is equal to minus 4, which implies that L21 is equal to minus 4. L11 we just calculated, 2.236, which is minus 1.789. L31, L11 is equal to 1. Again, this implies that L31 is equal to 1 over again L11 2.236, which is 0.447. Finally, for this L41 L11 is equal to 0, which implies that L41 is equal to 0 over 2.236, which is 0. Don't need to divide 0 by 2.236, but we just want to demonstrate that there is a pattern here. You divide by the same number. So you're going to see a similar pattern in all the next entries also. Not the same pattern, but similar pattern. So this pattern will then convert to a certain kind of a formula, which is then programmed into the computer. We are going to do it by hand, so we don't need to consider that formula. Now, this job is done. All these values are done. Now we come to the next. L21 square plus L22 square is equal to 6, which implies that L22 is equal to 6 minus L21 square. L21, we have this minus 1.789 square, and then you have to take the under root, and this is 1.673. You'll be taking the square roots in the diagonal elements. Just take the positive value. L31 L21 plus L32, now we're talking about this one, L32 L22 is equal to minus 4, which implies that L32 is equal to minus 4 minus L31 into L21. This is L31, this is L21. L31, this is L21. 0.447 into minus 1.789 over L22, we just calculated 1.673, which is L32, which turns out to be minus 1.913. And this one, L41 L21 plus L42 L22 is equal to 1, which implies that L42 we are interested in. L42 is equal to 1 minus L41 L21. L41 is 0. L21 minus 1.789 over again L22 1.673. Again a pattern develops, except this diagonal term. This is again a pattern, and the diagonal terms themselves will have a pattern. This turns out to be 0.598. So we have done 1 2 3 4 5 6 7. We need to do 2 more, and then our step 1 will be over. Now the next that we need to take up is L31 square plus L32 square plus L33 square is equal to 6. L31 square plus L32 square plus L33 square is equal to 6, which implies that now we are going to calculate L33, the next diagonal term. So there will be a square root involved. 6 minus L31 square, which is 0.447, minus L32 square, which is minus 1.913 under root. We are talking about, this is L31 and this is L32. Simply putting in the values. So as we proceed along, we can make use of the values that we have previously calculated. This turns out to be 1.463, and the next one, L41 L31 plus L42 L32 plus L43 L33 is equal to minus 4. Let's get this out of the way. L41 L31 plus L42 L32 plus L43 L33 is equal to minus 4, which implies that L43 is equal to minus 4 minus L41 L31. L41 0, L31 0.447 minus 0 into 0.447 minus L42 L32. Now we have L42 0.598, L32 minus 1.913, 0.598 minus 1.913 over divided by L33. L33 we have just calculated 1.463, and this turns out to be minus 1.952. Now only one value is left, and that is this one. L41 square plus L42 square plus L43 square plus L44 square is equal to 5. L41 square plus L42 square plus L43 square plus L44 square is equal to 5, which implies that L44, again a diagonal element, so we need to do this, take an under root here. 5 minus L41 square 0 square minus L42 square 0.598 minus 43 square minus 1.952, taking the under root and taking the positive value, and that turns out to be 0.912. Now your step 1 is complete. Basically all it needs is to write down the lower triangular matrix and the upper triangular matrix. Now using all these 2.236, we can just copy these here. 2.236 in the same order that we did 0.4470. Now you have 1.673 minus 1.913, 0.598. Then you have 1.463 minus 1.952, and this is your 0.912. So this is your lower triangular matrix. Here you have zeros, and the next one is simply the transpose of the same thing. 2.236 minus 1.789, 0.447, 0. Here you have 1.673 minus 1.913, 0.598. Then you have 1.463 minus 1.952, and at the end you have 0.912. This is the principal diagonal. Everything below it is 0, and this multiplies by u1, u2, u3, u4. Remember, this product is nothing but k. You have 0, 1, 1, 0. This is L, T, E is equal to F. Now, this was step 1 completed. Step 2. Step 2, we make this as x. So we basically write this as 2.236 minus 1.789, 0.4470, 1.673 minus 1.913, 0.598, 1.463 minus 1.952, 0.912. These are all zeros. You have x1, x2, x3, x4 is equal to 0, 1, 1, 0. It's very easy to calculate the values of x4 to x1 by backward substitution, by forward substitution, I beg your pardon. So if you please confirm these, first you calculate x1, which is simply 2.236 into x1 is equal to 0, so x1 turns out to be 0. The next one is this material of x1 plus this material of x2, and the rest are 0, is equal to 1. And this turns out to be x2 turns out to be 0.598. Please check these values. The next calculation, this material of x1 plus this material of x2 plus this material of x3 is equal to 1. X3 you want to find, x1, x2 are already known, put in the values. So x3 turns out to be 1.463. And finally 1.465, sorry. And the next one, x4, that turns out to be, putting in the values, you'll have to now do 0 doesn't count, but 0.598 into x2 minus 1.952 into x3, 0.912 into x4 is equal to 0. Put the values of 1, 2, 3, x1, 2 and x3, and you get x4, which is 2.743. So your x is 0, 0.598, 1.465, 2.743. But this was just an intermediate step. We are not interested in x, we are interested in basically u. But what is u if it is not LTU is equal to x? If you have a relationship between x, this is x basically. This part is x. So now we equate these two, and we should be able to calculate the value of u1 to u4. So just bringing in the transpose of the lower triangular matrix here now. All these values are 0, and here we have u1, u2, u3 and u4, and these are the x values we have just calculated. This time we are going to employ the backward substitution, because now this is just one number, multiply by u4, you get this, and then you go up one step at a time, and you calculate in the reverse order. So please confirm these calculations. You get u4 is equal to 3.008. The next step is u3, this multiplied by u3 plus this multiplied by u4 is equal to this number. u4 is already known, u3 can be calculated. Then you have u2, next step forward, backwards to be precise, and then u1 turns out to be 3.010. So this is what we started the problem for. Actually u was what we wanted to calculate. Now you will notice that there are some numbers after decimal here. These are nothing but what is called numerical error. There's nothing wrong with our algorithm here. We haven't made any mistake. Please recall that this was under root of 5. So we use a decimal instead of keeping that under root. So we lost some information here. Similarly, all these numbers, we are not using double precision here. So what happens is that in every step you are going to lose some information, and then you multiply them with each other. So in the end you will get this sort of an error. But very obvious to say that actual values are nothing but these. So this brings an end to our demonstration of the Cholesky method to solve our FE equations. This was a 4x4 matrix, but the same approach can be used for a matrix of any size, and it's very obvious to see that because the K matrix is symmetric, Cholesky is ideally suited for this sort of a problem. Thank you.